Today we are going to start with a new chapter, and this is the chapter of IT and communication. Now when we talk about this chapter, this is a chapter which is very different from many of the other chapters that we have seen, because this is not a chapter which has a continuous flow. What I mean is that there are a lot of topics which are separate from one another that have to be studied here. The first part will look to be very much connected, but when we move on to the second part of this chapter, you'll see that there are a lot of topics that we are dealing with which are completely independent of one another, which have no bearings of another topic or another chapter. So this is how we are going to go in this particular chapter. So to start with, the very first thing that we need to understand is its importance from both prelims as well as from mains perspective. Now, if you dive into the previous year's prelims question papers, you will see that questions from here have been coming regularly. In one form or the other, there have been a lot of questions that have come from here, and we'll take certain examples as well to understand what kind of questions have come in the past. But when you go to the mains examination, there you'll find that questions really have not come from here. We haven't seen a lot of questions coming in the past, but it doesn't say that there will be no questions in the future. So you have to be prepared for it, and we'll have a discussion on how certain questions can come from few of the areas that we are going to look into in this particular chapter. Alright, so that's why for now, going according to the pattern, going according to the history of your examination, I can definitely say that in the prelims examination, this has been an important chapter. So the very first thing that we need to understand in this chapter is about wireless communication. Now, when we talk about wireless communication, what is the meaning of wireless? The meaning is very simple for you. Anything or any form of communication that is not using wires. If you are using any form of communication where wires are not involved, then in that case you will say that it is a wireless communication. The simplest and the easiest perhaps of the examples is your mobile phone. Your mobile phone does not use any wire. You are not connected to any wire. You don't have to be fixed at a place while you are talking on the phone. So that's why mobile communication or mobile phones are one of the easiest examples to think of when it comes to wireless communication. Correct? So that's why communication systems that are not connected by wires of any kind will be called as wireless communication. Now there are many types of wireless communication that we see today. For example, you have infrared, you have Bluetooth, you have NFC or near field communication, you have Wi-Fi, you have Li-Fi, and there are others. For example, you have RFID also is one of the kind. So that's why there are a lot of ways in which wireless communication can be established in today's world, but these are some of the examples. So when we talk about wireless communication, now that it is happening without any wires, there should be some mechanism. There should be something behind this kind of communication to happen. What is that? That is electromagnetic waves. So most important component of any wireless communication is electromagnetic wave. And there could be many kinds of electromagnetic waves that perhaps we could use for wireless communication. Now, for example, when we talk about mobile phones, there is one part of electromagnetic waves, one of the entire spectra of electromagnetic waves that we use in mobile phones, and that is radio waves. So radio waves are used for mobile communication. Similarly, there are other forms of communication as well which are happening with the help of radio waves, which is a component of electromagnetic wave. So what do we mean by an electromagnetic wave? There are two words that you see here, correct? Electro and magnetic. What's the meaning? What do we mean by electro and what is the meaning of magnetic? Understand this. This electro basically is coming from electricity, or I would say from electrical, and this is coming from magnetic, correct? That's why when we are talking about a kind of wave that has electrical and magnetic components, it will be called as electromagnetic waves. I'm trying to put things simply here, not going into the exact definition of what electromagnetic wave is. So if we talk about the definition as such, what the definition could be: electromagnetic waves are produced when an electric field comes in contact with a magnetic field. Alright? Electric field coming in contact with magnetic field. How do they come in contact? Whenever they come in contact, we can see something like this. If you look at this particular figure, electric field or oscillation will happen in one direction, magnetic field direction will happen in another direction, and this another direction is 90 degrees or at right angles to the electric field. That is, if electric field is standing upright like this, then magnetic field is on the ground like this. So they are making an angle of 90 degrees between them. Alright. In such a case, the propagation of such a wave, the wave that comes out due to the interaction that is happening between electric field and magnetic field here, will be called as electromagnetic field. And this electromagnetic wave propagation will happen in a direction which is 90 degrees to both. Meaning that if I am like this, or let's say if electric wave is like this, electrical wave is like this, magnetic wave is like this, then in that case, the propagation of electromagnetic wave will happen in a third direction, which is 90 degrees to both electrical as well as magnetic fields. Just imagine a room. In a room, you have a length, you have a breadth, and you have a height. Correct? So if length is represented by electric field, breadth is represented by a magnetic field, then the height will be the direction of propagation of electromagnetic waves. So this is what has been shown in this figure as well, that electric field propagation is happening like this, magnetic field propagation is happening like this, and the propagation of the electromagnetic waves is happening in a direction which is 90 degrees to the propagation of both electrical as well as magnetic fields. So this is how electromagnetic fields will propagate. Now for the propagation, what you just saw in your diagram was that there are these kind of wave-like structures. Correct? This kind of wave-like structure is how the propagation of electromagnetic waves would happen. Now there are two terms which become very, very important whenever we look at any wave, or especially when we are looking at the electromagnetic waves and the propagation of electromagnetic waves. So these two are wavelength and frequency. So understanding of what wavelength means and what frequency means becomes very, very important. So what is the meaning? Let's try to understand the meaning of wavelength and frequency. Look at the diagrams given here. You have two figures that you can see. One, where the propagation, you can see everything is very congested, correct? Very close to one another. When you look at the other figure, which is below the first figure, you can see that here they are spaced out well. They have a space that you can see there. So this is how actually you can see what the meaning of wavelength is. Wavelength is the length of the wave between same points on a line. What do I mean? If I start from here, alright, if I start from here, I go up, I go down, and I come back to the same point. This will be called as one wavelength. This will be called as one wavelength. Similarly, let's say if I start from here, I go all the way down, I come all the way up, and I end here. Alright. So in this case also, this will be called as one wavelength. So I'm talking about coming back to the same point. So that's why here this is one wavelength. If I start from here, I have to come back to the same point. Similarly, if you look at the second figure, you will see that here the definition of one wavelength, if I start from here, it goes all the way down, I come all the way up, and I end here. So this will be one wavelength for me. So this is how we define wavelength. Now, what do you see as a difference between the two figures? The wavelength of the first figure, let me call it as figure A and figure B. So wavelength in the case of first figure is very small, correct? Wavelength is short. In the second one, the wavelength is long, correct? So that's why the first one, they will be called as short waves. They will be called as short waves. And the second one, they will be called as long waves. So this is what wavelength basically means. Now there's another concept that you see here. This is frequency. What is the meaning of frequency? The meaning of frequency also is very simple. How many waves can you accommodate in a given span of time? Let's say if I'm talking about 1 minute, how many waves can you accommodate in a given region in a minute will be called as its frequency. So if you look at these two figures, let's say if I'm talking about a span of time between t equal to 0 being here, t equal to 0 being here, and t equal to, let's say, 10 seconds being here. Alright. Now just count the number of waves. I'm counting the first one. Starting from here, going all the way down, coming all the way up. 1, 2, and almost 3. So I can count 3 wavelengths here. Right? Now look at the second one. I start from here, I go all the way up, I come all the way down, and almost 1. So this is just 1 wavelength. So what do you observe from here? Whenever you have a short wavelength, you have high frequency. Because here the number of wave count is high. And when you have long wavelength, you have very low frequency. Something that you can see here. That frequency count is just 1. And in this case, frequency count was 3. So short waves would mean what? Would mean high frequency. And long waves would mean what? They would mean low frequency. Alright? So that's the rule. When frequency is high, wavelength is short. When frequency is low, wavelength is long. Correct? So look at the definitions. A wavelength is the distance between 2 consecutive peaks, or even I can call it as 2 consecutive troughs of a wave. The distance is given in meters or fractions thereof. So that's why, because we are just counting the length, whenever you count length, you count it in meters. So that's why when you count wavelength as well, you will count it in meters. Similarly, if you look at frequency as a concept, what is frequency? It is the number of waves that form in a given length of time. It is usually measured as the number of wave cycles per second, or hertz. Alright, so hertz is what? Hertz, it's basically the number of wave cycles per second. So that's why frequency will be measured in hertz and wavelength will be measured in meters or millimeters, centimeter, micrometer, whatever you want. So that's why this can be called as 3 hertz and this can be called as 1 hertz. So this is how we represent wavelength and frequency. Now what is the importance of these two concepts? Whenever you come across any kind of electromagnetic wave or any kind of communication that is using electromagnetic waves, you will find the application and you will see that everywhere the frequency and the wavelengths will be mentioned. For each and every kind of communication that we are about to study, you will see that the mention of wavelength and frequency is done there. Even in the questions that have come in the past, the mention of wavelength and frequency has been done. So that's why that should be the first concept that you understand before jumping on to the specifics of different kinds of concepts or different kinds of communications that we'll see. So if you look at this particular figure, this is the entire spectrum of electromagnetic wave. Alright, electromagnetic waves can be distributed among different parts, starting from gamma rays, then X-rays, then ultraviolet, then comes the visible light part, the most important part, the one which enables us to see the entire world. Then after that comes infrared, and then after that radio waves. In between there is another one which is called as microwaves. Alright, so this is the entire spectrum of electromagnetic waves. Now all these electromagnetic waves have very specific use. So for example, when you talk about radio waves are very often used for different kinds of wireless communication, and this is where we are going to be focused on more, because for communication you will see that radio waves are very often used. Apart from that, others are also used. For example, infrared rays are also used for communication, but you will not find their application as much as radio waves. When we come to the other part of the spectrum, for example, when we talk about gamma rays or X-rays, they have completely different applications. So for example, gamma rays, you might know that gamma rays are used when it comes to medical applications. For example, in treatment of cancer, use of gamma rays is done. So that's why these kind of rays or this part of the electromagnetic spectrum is used in a very different manner as compared to the other part of the electromagnetic spectrum. Now, when we talk about these all different kinds of electromagnetic waves, just see this, that wavelength at this point is very short. At the end of gamma rays, we are saying that wavelength is short. And when you go to the other end, at this end you see that the wavelengths are very long. So radio waves are long wavelengths and gamma rays are very short wavelengths. So this is what we are going to understand as the specifics. One by one, each of the part of the spectrum we are going to study now. First, you have radio waves. So radio waves, the lowest range of electromagnetic spectrum, frequency up to about 30 billion hertz or 30 gigahertz, and wavelength greater than about 10 millimeters. So wavelength is greater than 10 millimeters. That is the longest of the wavelengths. So used primarily for communications, as I already told you, whether it is voice or data or entertainment media or anything. For all the different kinds of communication, whether one-way communication or two-way communication, for all these we will be using radio waves. After radio waves, you have microwaves. So microwaves fall in the spectrum between the radio waves and the infrared waves. Frequency 3 gigahertz up to 30 trillion hertz, and wavelength about 10 millimeters to 100 micrometers. Alright, so now you are decreasing the wavelength. Used for high bandwidth communication, radar, and also a heat source for microwave ovens and industrial applications. So all these are the ways in which we can use microwaves. After microwaves come infrared rays. Infrared rays basically lie between 30 terahertz and up to 400 terahertz. Wavelength between 100 micrometer and up to 740 nanometers. Invisible to human eye, but we can feel it as heat if the intensity is sufficient. So that's why you might have heard of infrared cameras. What you would see is that infrared cameras actually capture the heat signatures. So because they capture heat signatures, that's why we understand that now the heat signatures that they capture, they actually are capturing infrared rays. So whatever red colored pictures, if you have seen any infrared camera pictures, you'd see that there are reddish kind of pictures that they pick up. So those are nothing but the heat signatures or the infrared rays that are being emitted by different bodies. So if the intensity of heat is high, you would be able to at least observe infrared rays. You will not be able to see them. You will be able to observe them as heat. It will appear as heat. So this is what infrared rays are. After infrared, we come to the most important perhaps part for us, that is the visible light. Now visible light is being called visible because this is the part of the electromagnetic spectrum that enables us to see the world. If this part of the electromagnetic spectrum was invisible to us, we will not have been able to see the world as we do today. So that's why it becomes a very, very crucial part for us to see. Now, so for example, let's say even if you are watching this lecture on your tablet or any device, then in that case, you know that whatever you are able to see, you are able to see only because of this part of electromagnetic spectrum. If let's say this communication was happening through infrared rays or ultraviolet rays or radio waves, I would be invisible. Because there are lights in this room where I am recording this lecture, and this light basically is emitting the electromagnetic waves of this particular wavelength. That's why you are able to see me. That's why I am able to see the camera in front of me and I'm able to record this lecture. Alright. So this basically frequency 400 terahertz to 800 terahertz and wavelength between 740 nanometers to 380 nanometers. Now this figure will change a bit. If you look at 10 different sources, you will see that sometimes they will write 400 nanometers, sometimes they'll write 375, sometimes 380, sometimes 740 will become 750, sometimes 730. So these kind of small changes will happen, but more or less this is the range that we are talking about. Now, after visible light, you have ultraviolet rays. Ultraviolet rays, they lie between the visible light and the X-rays. Frequencies between 8 into 10 to the power of 14 to 3 into 10 to the power of 16 hertz, and wavelength between 380 nanometers to up to 10 nanometers. So we are increasing the frequency and we are decreasing the wavelength. Now, when we talk about the ultraviolet light, I'm very sure that you are very much aware that this is a part of sunlight. Sunlight that is incident on the earth, it has the components of ultraviolet light. Now ultraviolet light, actually there are three different kinds of ultraviolet light. You have UVA, you have UVB and you have UVC. These are three different types of ultraviolet light. Now when we talk about ultraviolet light, the application of ultraviolet light, you will see that there are many medical and industrial applications, but it can damage living tissues. Now, ultraviolet light, you might have heard in different ways, the usage in different ways. For example, something which is very, very easy example is for killing microbes or killing bacteria. So, for example, let's say if you have water filters. So, some of the water filters will tell you that they are RO plus UV plus UF kind of water filters, right? You might have heard of this RO plus UV plus UF. So here the UV part basically is ultraviolet. Why ultraviolet? Because ultraviolet will be able to kill the living germs or kill the bacteria, etc., which are there in water. RO or reverse osmosis will not be able to do that, killing of the microbes. But ultraviolet can. So that's why ultraviolet rays are used in these kind of filters to kill the microbes or kill the bacteria. So there are many such applications for which ultraviolet light is being used. But they can be damaging to the tissues as well. So for example, you can get sunburn from ultraviolet light. If there is an overexposure to ultraviolet light, it can even lead to cancer in people. So that's why we have to ensure that we do not get overexposed to ultraviolet light. So now there are three types of ultraviolet light, right? There is, as I said, UVA, UVB and UVC. Let's try to understand them one by one. First is UVC or ultraviolet light C. So this is basically between 100 to 280 nanometers. Now this is the shortest of the wavelength of the three forms of wavelength and most harmful of the UV radiations. But the good news for us is that this is a part of ultraviolet light that is completely absorbed by the ozone layer. There is no component of ultraviolet light that naturally gets to us through sunlight, because the ozone layer of the atmosphere helps in saving us from ultraviolet light. Now, it's not that there are no man-made sources. For example, people who are working in welding industries, they are very often exposed to ultraviolet light C. So that's why they have to keep a shield with them so that they do not get overexposed to ultraviolet light C. So that's why in welding torches, in mercury lamps, in germicidal UV lighting, in all these cases, we see that ultraviolet light C or UVC is present. So that's why we need to make sure that we do not get overexposed to ultraviolet light C. After this, you have UVB. Now UVB has a longer wavelength as compared to UVC. The wavelength lies between 280 to 315 nanometers. Now this is a part which is lesser harmful as compared to UVC, but still more harmful as compared to UVA. Again, the good news is that almost 95% of UVB gets captured and gets blocked by the atmosphere. Almost 95%. So only a very small amount of UVB is able to penetrate through the atmosphere and reach the surface of the earth and be incident on our skin. But this can be a very major cause of sunburn because this is shorter wavelength and is more harmful, is higher in energy content as compared to UVA. So mostly absorbed by the ozone layer, but still gets through. About 5% gets through overall. Harms the top layer of the skin in even 15 minutes of sun exposure, and it can age skin over time. So that's why we have to ensure that we do not get overexposed to UVB. Then you have UVA. Now UVA is the longer part of the wavelength, or rather I can say that the longest part of the three wavelengths or three components of ultraviolet wavelength. The wavelength lies between 315 to 400 nanometers. Now, one thing that you have to remember is that vast majority of UVA is able to penetrate through the ozone layer. So almost 95% of UVA reaches the surface of the earth. Only about 5% gets blocked. So this is the component of the ultraviolet light that can be the most harmful for us because we can get largely exposed to it. We do not get exposed to UVC naturally. We get exposed to UVB only in a very small amount, but we get exposed to UVA in a larger amount. So that's why this can be very damaging for the tissue if you have been in the sun for a very long time. That's why you would use things like sunscreens, etc., to save your skin from overexposure to UVA. So it is a form of radiation that causes skin aging like spots and wrinkles because it does reach so deeply into our skin. UVA rays can tan skin and do appear to be linked to cancer. And can penetrate through glass and clouds, causing harm even on overcast days. So that's why you have to remember, even if the rays of the sun do not reach the layer of the earth or the surface of the earth, at least the radiations or the ultraviolet part of the radiation does reach the surface of the earth. So these are the types of ultraviolet light. After ultraviolet, you have X-rays. So now when we talk about X-rays, X-ray is a component that starts just after the ultraviolet light, but also coincides with the wavelength of gamma rays as well. There are two types of X-rays, one called as soft X-rays, the other one is called as hard X-rays. Alright, there are two types. You have soft X-rays and you have hard X-rays. Now when we talk about the soft X-rays have a particular band, and this band is between UV rays and gamma rays. They do not overlap with gamma rays. The other one, that is hard X-rays, they overlap with gamma rays. So soft X-rays, frequency 3 into 10 to the power of 16 to 10 to the power of 18 hertz, wavelength between 10 nanometer to up to 100 picometers. Hard X-rays occupy the same region of electromagnetic spectrum as the gamma rays. Only difference between them is their source. X-rays are produced by accelerating electrons and gamma rays are produced by atomic nuclei. Alright, so accelerating electrons and atomic nuclei, this is the only difference. So we have discussed about this when we discussed about nuclear energy. In nuclear energy chapter, we had discussed about the fact that when we talk about gamma rays are a part of, or gamma radiation or gamma decay is also a part of radioactivity. Where is radioactivity starting from? From inside the nucleus. When the nucleus is very heavy, it is not able to contain all the protons and neutrons together. This is where gamma rays can be emitted as a part of the process of radioactivity. We have discussed this. Even in nuclear fission and fusion also, gamma rays can be emitted from there. But in all these cases, it is coming from inside the nucleus. But when it comes to X-rays, X-rays are produced by accelerating electrons. So that's why they are not being produced from inside the nucleus, but rather from outside the nucleus, but inside the atom. So this is the basic difference between X-rays and gamma rays. Although they occupy the same part of the electromagnetic spectrum, still they are very different in characteristics because of their origin. Alright. After X-rays, you have gamma rays, the last part of the electromagnetic spectrum. Gamma rays are in the range of electromagnetic spectrum above the soft X-rays. Frequencies greater than about 10 to the power of 18 hertz. Wavelength of less than 100 picometer. So gamma rays causes damage to the living tissue, which makes it useful for killing cancer cells when applied in carefully measured doses to small regions. So that's why, because gamma rays can be very, very harmful for the skin or for the tissues, they can very easily degenerate the tissues. So that's why they have to be used in very particular ways. They have to be used in a very targeted manner, so that only the cells which are affected, they should be targeted. Other cells should not be harmed at all, because whatever cell is exposed to gamma rays, it will get destroyed or burnt because of exposure to gamma rays. So that's why uncontrolled exposure is extremely dangerous to humans. So that's why we have to ensure that overexposure to gamma rays does not happen. So this is about all the different parts of the electromagnetic spectrum.